Good morning, good afternoon. Thank you for attending the online AWS Summit for Europe, Middle East and Africa. In this session, I'm going to talk about AWS Networking, the core networking service that you can use to host your infrastructure, to deploy your application. I'm going to talk about VPC, subnets, IP address, IPv4, IPv6. We are going to talk about security with network access control list, NACLs and security groups. We are going to talk about load balancer, and I will finish this talk. The last 15 minutes of this talk will be around CloudFront, Amazon CloudFront, the content delivery network of AWS to help you to scale your content distribution globally. My name is Sébastien Stormac. I'm developer advocate in the European team based in Paris, as you might have heard already from my French accent. So let's dive into AWS networking. The basic building block for AWS networking, it's called a VPC. It's a virtual private cloud. And a VPC, it's a bit like the network you use to manage inside your data center on premises, but it's virtual. It's a configuration on our side that will isolate a part of our network for your usage. So a VPC spans multiple availability zones inside one region, but it sticks within one single region. And you can create multiple VPC for many different applications. Inside the VPC, you're going to create subnets. A subnet, as the name indicates, it's a part of a VPC, and a subnet stays within one single availability zone. They cannot span across multiple availability zones. So typically you're going to create public subnets where you're going to host the resource that need to receive connection from the internet, and private subnet. A resource that will be hosted inside subnets is typically Amazon EC2 instances, virtual machines, or databases such as Amazon RDS databases. So within the subnet, you can create multiple resources. You just need to be sure that the subnet is large enough to accommodate all the resources, that it has enough IP address for each of the resource. So a VPC, a network without any gateway to other network would be quite dull. So of course you have different connectivity options. You have peering options to connect to other VPC. I'm going to go into much more details in a minute about that. We have a variety of gateways, of endpoints that allows your application to connect back securely and at scale with other AWS services to route the traffic in and out your VPC. So let's have a look at basic web application. A basic web application will be probably over multi-tier, so like your web server tier, your application server tier, and the web server will be in a public subnet because it needs to receive connection from the internet. The application server, you don't want to receive connection there to accept connection from the internet, so you are going to put that application server in a private subnet, and I will explain the difference between the two in a minute. The first thing you need to create a VPC and subnets is to define the addressing. And there are a couple of things to think about when you think in terms of IP address for your VPC. First, you cannot change that after you created the VPC. So it's better to get it correct from the scratch, otherwise you will need to delete the VPC, which implies to terminate all the resources running inside the VPC and to create a new one with the correct IP address that you want. The IP address are defined by ranges of IP address. We call that CIDR range. It's not the name of a fancy drink. CIDR stands for classless interdomain routing. Maybe if you have gray hairs like me, you've been at school and you learn about different classes of network, class A, B, C. Today we are not counting, or we are not referring to IP network like that. We use a fixed notation to delimitate the bits and bytes that are part of the network number and the bits and bytes that are part of the host number. And you indicate with slash and a number the number of bytes that are fixed for your network, that are the network number. So for a VPC, you can go from a network as large as /16 out of a 32 bits address. It means that you have 16 bits available for your host, which is a bit more than 65,000 hosts, or your network network can be as small as /28, which means out of the 32 bits IPv4 address, it would be only 4 bits available for the host. 4 bits means 16 hosts available for you. So in this example, going back to our network, I will assign a CIDR range, let's say 172.31.0.0.16, and then I will assign part of that range for each of the subnets. So the first subnet has decided to take the range 0/24, so I still have 8 bits available for my host. That's 256 hosts minus the reserved IPs, roughly 256 hosts. .1 for the second subnet, .128 for the third, and 129 for the fourth one. There is no rules here, it's just me choosing this number. I could have done also 0, 1, 2, 3 or 1, 2, 3, 4. It's really up to you. What about IPv6? I hear your question from here. And VPC also support IPv6. You know that IPv6 are represented with extet numbers separated by colon. And there is also the /something. /64 means there are 64 bits for the network and 64 bits for the host. 64 bits for the host, it's quintillion of hosts, it's really huge number, to exponent 64. There are 2 special addresses that you need to pay attention: the local link address, the link local address, sorry, LLA, which is the address attached to your network interface, and the global unicast address, which is the equivalent of a public IPv4. It's the public routable address for your network interface. Let's have a look at a dual stack Amazon EC2 instance, Linux Amazon EC2 instance running on a VPC with IPv4 and IPv6 address. You can see it has an IPv4 address, it's the private address of the subnet, 172.31.0. It has also the link local address, and it has an IPv6 global address, GUA. One big difference between IPv6 and IPv4 inside your VPC is that you cannot choose the size of the VPC. With IPv4, you can choose between /16 and /28. With IPv6, the VPC size is fixed at /56, and the subnet are fixed at /64, which leaves you 64 bits for the host address, which is more hosts than you probably will never need during your lifetime, or at least the lifetime of your VPC. So where to use this IP address? It's just like IPv4. I assign a range for my VPC and then a sub-range for each of my subnet, and I choose arbitrarily the part of the sub-range that I do allocate here. Okay, now we have the basic VPC, the subnet, and the addressing. What can I do, or what do I need to do if I want to have public IP connectivity for an Amazon EC2 instance running in one of these 2 subnets? You need five different things. One of them, you need to have a public IP address. All IPv6 addresses are public, so if it is an IPv4 address, it has to be a public one and not one from the VPC, because the one from the VPC are private. You need a way to route your traffic to and from the internet. So for that you need 2 elements, an internet gateway and a routing table, and then you need security groups and a network ACL that allows the traffic to flow in and out your instance. So let's dive into the details of these 5 points that you need to get internet traffic on your Amazon EC2 instance. The public IP address first, IPv4, by default, you can enable a flag on Amazon EC2 to ask to receive an auto-assigned public IP address. It's easy, but if you stop and start the Amazon EC2 instance again, the IP address will change. Is it a problem? It depends. If it is a web server that is expected to receive incoming connection from the internet, having a different IP address after a restart might not be the good things. Okay, you can work around that. You can create a small script that you will install on the instance, and at boot time it will look up the IP address and register itself to a DNS server. But it's not very convenient, and you do not control how much time it takes for a DNS cache to propagate. So there is alternatives to have a fixed IP address. It can be either an Amazon Elastic IP address, or you can bring your own IP address. So Amazon Elastic IP address, the idea is that you reserve an address for your account. So you take one of the many public IP address from AWS and you reserve it for your account. And once you have that IP address, it's assigned to your account. We're not going to remove it. Then you can assign that address to a network interface. So even if you destroy, delete, terminate your Amazon EC2 instance and recreate a new one, you can reattach the Elastic IP address to the new network interface of your new Amazon EC2 instance. And that way you keep a stable IP address over time. Bring your own, it means if you have your IP address already registered for your company, you can use this IP address, and we are going to route the traffic towards this IP address in your VPC. So in this example, I'll take auto-assign public IP address 5456 for the web server in subnet A, and 5221 for web server in subnet 2. We have one out of list of 5 things complete. Point 2 and 3 in my list is to get to be able to route traffic outside towards the internet and to receive incoming connection. And for that, you need an internet gateway. So the internet gateway is not a device, it's just a configuration in our networking gear that will tell us that your VPC is actually connected to the internet. It can send packet to and receive packets from the internet. Because it's not a device, there is no concern of scalability or high availability. You just create an internet gateway in the console and you attach it to your VPC. Once you have the internet gateway for the subnets where you want to have connectivity with internet, you add a line in the routing table, a line that says any traffic to an IP address of the internet, in IPv4 it means 000/0, the next hop is the internet gateway, so the destination is the internet gateway. And if you are in dual stack with IP4, IP6, you need to do the same for IPv6 address. So if you do that and attach that type of routing table that you can see on the right side of the slide, then you will have internet connectivity for your subnet. We also have an egress only internet gateway. So this is only available for IPv6. It's an internet gateway that can send open connection to the internet, but not forward packets, incoming packets. So you cannot receive a connection from the outside, but you can start a connection from your resource inside the subnet. You can create an egress gateway, attach it to the VPC, and change the routing table just like with the internet gateway. Pay attention to the last 2 lines of this routing table on the right side. If it is an IPv4 address, we are sending the traffic to the internet gateway. If it is an IPv6 address, we send the traffic to EIGW, the egress-only internet gateway. So what makes the difference between a public subnet and a private subnet? It's just the connectivity to the internet. So the only difference is a public subnet has a routing table with a route that allows to send traffic to the internet or to receive connection initiated from the internet. A private subnet has no such line in the routing table. It can only route traffic between the other subnets of the VPC. That's the local target that you can see in these routing table. And beside that difference, all the rest is the same. So a subnet is a subnet. What makes it public or private is just the routing table attached to it. But what if you have a resource in a private subnet that needs to communicate over the internet? I told you that thanks to the local line in the routing table, a resource in a private subnet can communicate with any other subnet. So your web server can call your app server, and the other way around. The app server can call the web server by default. But what if that instance A needs to actually connect to the internet? And why do you want to do that for an app server? Maybe just for a software update. If you type sudo yum install or sudo yum update, you need internet connectivity. Same with npm install, with pip for Python. Or to connect to the Microsoft Windows update repository, you need an outgoing connection going to the internet. And you can do that with a NAT gateway. So NAT, it's network address translation, and it acts as a router. It will receive the packets from the instance A and route that packets towards the internet gateway and then the internet. And when the packets come back, the NAT gateway will do NATing in the opposite direction. So it will replace its own IP address as destination with the destination, the IP address of the instance A as destination, and forward the packet back to instance A. So if you want IP connectivity from private subnet, you can use the managed gateway. It's a managed service, so there is no Amazon EC2 instance to install or to manage, and we scale and we make the service highly available for you. So we have bullet point 1, 2, and 3 covered. What about 4 and 5? Network ACL, security groups, and this is related to security, so I'm going to talk also about VPC flow logs and Amazon VPC traffic mirroring. Network ACL, it's a stateless filter that filters all the traffic coming in and outside the VPC. So a network ACL is attached to the VPC subnet, and it filters all the traffic entering or leaving the subnet. Typically, a network ACL, it's a blacklist, so it allows everything by default. That's the good news. And if you want to restrict some traffic, then you are going to add some deny rule inside the network ACL. All the rules within a network ACL are analyzed one after the other, so the order is important because at the first deny, we block all the traffic and the rest of the rules are not analyzed. So for the web server, I want to authorize all incoming and outgoing traffic, so it's 0000/0 on all port is authorized, and the same for the inbound. So that's for outbound and for inbound. For my app server, I would like to be sure that the web server can only talk to the app server. And the app server, as you can see on the diagram, is listening on port 8443. So I will create a rule that only authorizes traffic if the destination port is 8443 and if the source is one of my addresses of the subnet, or actually the VPC 172.30.1. And because NACLs are stateless, if I create a rule that filter the incoming traffic, I need also to explicitly allow the outgoing traffic. And the outgoing traffic is the source port is randomly selected by the application server. So I have to open the whole port range from 1024 to 65,000 something and to any destination within my VPC. So it's the inbound and outbound NACL for my private subnet. Security groups are stateless, and it's a filter that works at the network interface level. So I like to give the analogy of a shield. When you launch an Amazon EC2 instance, you put it inside one or several security groups, and a security group, it's like a shield. So it protects the instance from any incoming connection coming to that instance. So if you want to authorize a connection to your instance, you need to open a hole in the shield. You need to configure the security group to actually authorize connection to a specific TCP port and from a specific TCP IP address or range of address. So for my web server, by definition, a web server should be available for anybody on the internet. So I will authorize any SSL connection 443 coming from 000/0 or the equivalent in IPv6. So anybody can connect to my web server. For the application server, I have to create a rule that explicitly authorizes 8443, the port of the application server, because otherwise no connection will be authorized to the application server. And look at the source there. Instead of giving the source IP address of the web server, which might change over time, remember if you are using auto-assign IP address, I give the reference of the origin security group. So basically it says any machine in that security group the security group of the web server is authorized to call to open a connection on TCP 8443. That's how security groups are working. You do not need to define the outbound filter because a security group is stateful, so it remembers that once a connection is authorized, it will automatically authorize the reply for the same TCP connection. If I want to filter on the outbound, by default outbound is open in a security group, so a machine can connect to anything else, but you can restrict that. Here is an example to restrict the app server to only call what? What is that? PL68, it's not an IP address, not IPv4, it's not an IPv6 address. It's a prefix list, and a prefix list, you can find them through the CLI using AWS EC2 describe prefix list. And this prefix list ID correspond to Amazon S3 endpoint addresses in US West 2 region. So by adding an outbound rule to my security group there, I'm telling that my application server can only initiate connections to Amazon S3 in that region. I see very few customers using outbound security groups rules, but they are there. You have to know it exists. It might be useful in some cases. So, now that we have the traffic flowing in and out, let's look at what we might get, how we can get some insight about that traffic. And VPC flow logs is one way to get some insight about the traffic. So VPC flow log will log the metadata of the packets going in and out, either your VPC or a specific subnet or a specific network interface, and it will log that on Amazon CloudWatch logs, or it will send text files to Amazon S3, and then you can analyze the content of these logs with tools such as Athena, for example. All that logging operation is disabled by default. You need to enable at the VPC level. It does not impact your latency or your throughput because that logging operation is made outside of your instance. It's not the instance, the operating system, which is generating these logs. You can choose to log all traffic which is accepted or rejected, for example, by a hacker or by a security group. And you only get the metadata. Look at the right side of the slide there. You don't have the content of the packet itself. If you want to analyze the content of the packet, you can set up VPC traffic mirroring, where you start another Amazon EC2 instance and you configure the network interface of that EC2 instance to be the mirror of an original network interface. So all traffic arriving to the original network interface will be mirrored to the other. And there you can analyze the packets. You can use appliance machine, appliance software application to do packet detection, intrusion detection system, intrusion prevention system, IDS or IPS. If you have multiple VPC and they don't share or they don't overlap in terms of IP range, sooner or later you are going to ask, how can I connect these VPC together? I would like one resource from one VPC to talk to the resource of another VPC. And you can do that by creating peering agreement. So you go into the console and you say, I am VPC1, I want to do a peering with VPC2. The owner of the VPC2 has to approve the peering as well. But once you do that, you have like a virtual gateway between the two VPCs that you have just paired. So you need to add a route inside the routing table of your subnet that says, if I want to connect to the IP address of the other VPC, then send the traffic as next up to the peering gateway. And of course, you need to do that in both VPCs so that the packets can flow in and out each of the two VPC. And then you do that one by one with all the VPC you want to pair. If you are pairing with multiple VPC, you need multiple lines in your routing table, depending on the subnet address of the VPC target address, you add a line going to the corresponding VPCX peering gateway, so for each of these network. If you have only two peering, like A is peered to B, A to B, B to C, it's not transitive. So A cannot talk to C in that scenario. You need to have an explicit peering agreement between all the VPC to be able to route traffic in and out between VPC. VPC peering works across multiple regions. It also works across multiple accounts. Of course, the account owner has to agree on the peering. A couple of things to remember about peering. You can reference security group from another VPC to define the rules inside your security group. Remember, the source IP address is not a hard-coded address in a security group. It might be just a security group ID that refers to another security group. That security group can live inside another VPC. You can also have DNS private name resolution to return private IP address across VPC, and peering works both for IPv4 and IPv6. I mentioned that already, but it's super important. You cannot have overlapping of IP address between your peer VPC, and if you have two VPC, you can only connect and have one peering between two VPC. It doesn't make sense to have two peering agreement between the two same VPC. Also, if you are using jumbo frames, these are going to be dropped at the regional boundary, so it does not work across inter-region VPC peering. I was talking to a customer the other day, south of France. They are managing many different accounts and they have 500 VPC, and managing the peering one by one between 500 VPC across multiple accounts and multiple regions was a nightmare for them. And that's why 2 years ago at reInvent 2018, we did introduce the Transit Gateway. So the Transit Gateway is like a virtual router inside a region. Instead of doing one by one peering agreement between your VPC, you connect your VPC to the Transit Gateway. And each VPC has only one connection to the Transit Gateway. The Transit Gateway will be able to route traffic in between your VPC. You can also use the Transit Gateway as a hub and spoke architecture. So you connect your different VPC to a Transit Gateway, and the Transit Gateway over VPN tunnel to your corporate data center. So if you do that, you need a routing table to the range of IP address inside your data center that points as a next step to the Transit Gateway. And on the Transit Gateway, you have a routing table that sends the traffic to the VPN tunnel, the VPN endpoint for that range of IP address. And it's the same idea if you have Direct Connect, so if you have a leased line between your data center and one of our Direct Connect location, you can connect multiple Transit Gateway, because you have one Transit Gateway per region, to a Direct Connect gateway and act as an hub and spoke architecture to connect multiple VPC from multiple accounts in multiple regions through one single Direct Connect back to your data center. Okay, we set up our sample web app. It wasn't really highly available. Our users were using direct TCP connection to the web server. So we could have some DNS round robin between the two web servers, but that would be a nightmare to scale. If we scale up, adding host, or scale down, removing host. So how can you address load on your web server? You do that by adding an elastic load balancer. The elastic load balancer allows you to distribute incoming traffic across fleets of Amazon EC2 instances, private IP addresses, containers running inside ECS or EKS, or even Lambda function. We have 3 types of load balancer. I will not talk about classical load balancer. For anyone that started to use AWS after 2014, it's not necessary anymore. So let's focus on the application load balancer and the network load balancer. The application load balancer works at layer 7, so it understands HTTP. It can take routing decision based on HTTP header, cookies, paths, query paths, for example, or parameter. It can route traffic towards EC2 instance, Lambda function, containers, private IP address. While a network load balancer works at TCP level, at layer 4 level, so it can balance traffic for TCP, for UDP. It can also act as a TLS termination endpoint, and it can route traffic to almost the same except a Lambda function. There are three components in a load balancer. The first is the listener. The listener is the part that is listening for incoming connection coming over the network. You might have multiple listeners for one load balancer. For example, TCP/80 for HTTP and TCP/443 for SSL. Then for each listener, you have a couple of listener rules that will define where to send the traffic depending on the content of the request. Remember, it's a layer 7 load balancer, so it understands HTTP. So based on headers, HTTP headers or paths, you can take different routing decision. Listener rules send traffic to one or more target groups, and inside the target groups you have targets. Why you would have more than one target group? It's very handy for things like blue-green deployment. You can attach two target groups to one rule with different weights, saying 80% of the traffic is going to go into that target groups and 20% of the traffic will go to that target group. So when you deploy a new version of your application, you can progressively shift traffic to the new version of your application. And if anything goes wrong in your deployment, it's very easy to reconfigure the load balancer to send the traffic back 100% back to the original version of your application. This is called blue-green deployment. I wrote a blog post about that. Just use your favorite search engine, weighted target group, AWS blog, and you will find the blog very, very easily. So in our final architecture, we have a load balancer. That's the endpoint that external customers are reaching to, and the load balancer sends the traffic to the web server. And of course, in that case, we don't need the web server to be in a public subnet with public IP address. We don't want anyone to bypass the load balancer and go directly to the web server. So we are going to move the web server to private subnets as well, and only the load balancer will stay in the public subnet. That's the only part of our infrastructure that is publicly available from the internet. It also helps to reduce the surface of attack for your web server, because there is no TCP connection allowed to them, except if it is coming from the load balancer. Wow, that was a tour of VPC, subnets, IP address, load balancer, transit gateway, internet gateway, many names in your head. We have many partners that can help you to design and to monitor your cloud infrastructure, your network cloud infrastructure. In the partner discovery zone, do not hesitate to visit the solution from VMware. I'm thinking about Cloud Health. It's a management and monitoring tool for AWS infrastructure and for your network. So know that you have we have our simple web application, which is defined. How are you going to scale that to distribute content to millions of customers globally? Because I wish you the best for your application. I'm sure your application will be successful, and you will have millions of clients around the planet. If it is your case, you probably want to cache part of your content close to your customer. You want edge network location where your customer can connect to, instead of sending all the customer to your load balancer. Sorry. The way to do that, it's called Amazon CloudFront. So CloudFront, it's the AWS Content Delivery Network. The idea is to provide a cache or an entry point into the network for your customer close to where they are, so they can connect with very low latency to these entry points. And then after that, the traffic goes through the AWS backbone, the global network of AWS. If we are talking about content, we can cache the content there. Otherwise, CloudFront just forward the request to an origin, and an origin might be your load balancer, it might be an API, it might be an Amazon S3. Actually, it can be anything. The origin can also be inside your on-premise data center. So CloudFront can work separately of all the other AWS services. Some customers are just using AWS CloudFront, and they put CloudFront in front of an existing infrastructure. We have more than 200 points of presence on the planet, POP, in many big cities of this planet, and we added dozens of that just last year. So the benefits for you is that you provide your content to your customer with a lower latency, because instead of connecting to your infrastructure, the customer are connecting to the closest point of presence. It has built-in DDoS protection. If someone attacks your infrastructure, it will actually attack CloudFront, and we have a massive capacity to answer that. So even before the request will reach your infrastructure, it's very high chance that the DDoS attack will be mitigated on the edge. So it has massive scale. It has many different ways to optimize the connection between the point of presence and your origin, making the traffic more efficient with lower latency between the point of presence and your origin. A couple of examples of new cities, new countries that we added last year. We had a point of presence in South America, in Bogota, in Brussels, in Lisbon, in Tel Aviv, to give a few European cities. More than 75 points of presence have been added in 2019, and we have consolidated total peering and transit connectivity over 150 terabits per second. That's the capacity, the global capacity of CloudFront. In every single city where we open a CloudFront point of presence, we see a dramatic reduction in latency compared to connecting to US East 1, for example, because customer connections are going directly to the closest point of presence. And you can see on this graph the reduction of latency to reach the local point of presence in Israel, in Bahrain, in Argentina, and in Chile. There are three main components for distribution, three names that you need to remember. A distribution, it's a unique CloudFront.net URL, so that's the starting point. If you want to use CloudFront, you need to create a distribution, and the distribution will give you a URL like abc123.cloudfront.net. Of course, you can bring your own domain and your own certificate there as well. But this is how you should refer to your content. So instead of using the ELB DNS name or your API endpoint DNS name or the Amazon S3 DNS name, you should use in your application, or you should distribute the DNS name of the distribution. This is where you are going to configure TLS. We do support HTTP v2, we do support IPv4, IPv6. We also can log all the traffic to Amazon S3. I'm doing that on my own blog post, on my own podcast, to analyze all the downloads that are made, and you can break down by a point of presence, for example. The second building block is called the origin. And the origin, this is where CloudFront is going to fetch the content. So it can be anything HTTP, doesn't have to be on AWS, can be on-prem or another cloud. So you can really use CloudFront as a standalone AWS service, not connected to anything else. But typically, in an AWS architecture, an origin will be a load balancer, or will be an Amazon EC3, an Amazon S3 address, for example. This is where you configure the TLS configuration, the TCP port, timeout to connect back to your origin. And then in between the distribution and the origin, you have the behavior, and the behavior is where you define the path, for example, where you say, okay, for that path or that type of request, I will go to that origin or to that origin. The type of HTTP method to support, get, post, delete, put, you decide. This is also where you are going to define the caching policy. So by default, the documents can be cached. This is where you are going to decide to whitelist or blacklist a couple of HTTP headers and cookies, for example. And this is also where you can define a Lambda on edge trigger, and I will talk about Lambda on edge in a minute. So CloudFront has quite advanced security possibilities with access control. It can help to verify header or ACL or signed URL. If you are connecting to an Amazon S3 identity origin, you can create an origin access identity that allows you to keep your bucket, your Amazon S3 bucket, private, and to authorize only CloudFront to access to that bucket. You can restrict content per geographic area or countries if you have content which is licensed that you cannot distribute outside of a specific country. It's something you can define at CloudFront level as well. And it integrates with our web application firewall or Shield service for advanced DDoS protection. CloudFront is not only for content, it works super well for API as well, because it allows to have your customer connecting to the CloudFront POP for API to terminate the TLS connection on the edge, and then to use optimized connection over the AWS global network between the POP and your actual API endpoint. And the further you are away from the region, the further your customer is away from the specific region, the higher is the benefit. Look at the number there. These are a reduction compared to connecting to US East 1. So someone in India, if he or she connects through the one of the local POPs we have in India, we'll see a reduction of latency of 93% compared to a connection to US East 1. Because we are using persistence connection, we are using connection pooling, we are using keep alive and many other TCP optimization techniques, and this traffic goes over the AWS global managed network. It's not going over the internet. One of my favorite features of CloudFront is called Lambda on Edge. So Lambda, it's a small piece of code, it's a function that you can write in Node.js and execute on the edge. So you can have a bit of behavior that you define on the edge. And there is no server to manage, no deployment to do. You just write your code, you click deploy, and it will be deployed across the edge location. And there are 4 different events that can trigger your Lambda function. Viewer request. This is every single request coming from CloudFront, but before it will check the cache, so you have a chance there to manipulate the cache key, for example. If there is a miss in the cache, then CloudFront will call the origin and, there is a second trigger called origin request, and that one is just before calling the origin. So this is where you can change the content, for example, when the content is not found in CloudFront and we need to fetch it again from the origin. At this stage, for example, you can change the attribute of the upstream request, for example, changing the URL or the origin domain name, or you can even generate content dynamically instead of going back to the origin. When the origin response, but before putting the content into the cache, we have the origin response event, which is triggered, and you have the possibility to alter the response. For example, if the origin return a 400 error message, or a 300 a redirect, or an authorization error, you can take action upon that. And then the last one is the viewer response. This one is triggered for every single request, and it's after the cache, before the content is sent back to the viewer. So there are many use cases for Lambda on Edge. For performance, you can manipulate the cache header, you can follow redirection, you can normalize the user agent, you can generate dynamic content by compressing, resizing image, or even render page inside one of these Edge functions. Some customers are using it as well for A/B testing, to test 2 different versions of a website and see which one is bringing the best performance in terms of whatever KPI you observe. It can be used for URL rewriting or to provide fancy, pretty URLs, to do failover between multiple origins, or you can use that for security. You can inspect HTTP header, check for the validity of a JWT token, a OO token. You can sign requests that are going to the origin to show to the origin that the request has been validated, and it can be signed based on user attributes, such as an OO token, for example. So there is a variety of use cases in terms of performance, security, that you can implement using Lambda on Edge. And we have many customers using CloudFront in many different industry segments. It might be financial institutions such as Intuit or HSBC. It can be e-commerce website, Amazon.com, of course, but the others that you can see on the list there on the right side of the slide. CloudFront is also very popular for gaming and, of course, for media and entertainment, where these companies are distributing a lot of content over the internet. In gaming, Supercell, Rovio, video, in media and entertainment, Amazon Video Prime, Spotify, Snapchat, or M6, Web M6. It's a private TV channel in France. So that's an overview, and that was a long overview. If you want to learn more about CloudFront, go to the AWS Training and Certification website. We have a 2 hours deep dive training on CloudFront. We also have a free 2 hours deep dive on the Transit Gateway. So if you want to learn more about the Transit Gateway, just head to AWS Training and Certification website, aws.training. It's super easy to remember. If you feel you want to validate your knowledge or to have your knowledge recognized by your peers, you can also register and pass the exam for Advanced Networking. It's a specialty exam about networking. So AWS Certified Advanced Networking Specialty Exam. Wow, that was a long presentation, 45 minutes, where I talk about network. We start with a very simple VPC and a couple of subnets. I talk about IP addressing, IPv4, IPv6. We talk about the different gateways that you can use to connect your VPC to other source, the NAT gateway, and so on. Then we talk about VPC peering and the multiple options you have to peer your VPC, either one VPC to one VPC, either through the Transit Gateway. We talk also about the load balancer to load balance request to a fleet of Amazon EC2 instance. And then I finish by showing you the benefits of using a content delivery network, Amazon CloudFront, and the multiple options you have to configure and to secure, to create a secure configuration for your application using, for example, Lambda on Edge. So thank you for listening to this networking talk. I hope you will enjoy the rest of the conference today with my colleagues. Do not hesitate to reach out to me to Sebsto, S-E-B-S-T-O. Thank you and see you soon.